Hello everyone and welcome to the Chemistry ASA level Cambridge video. Today we will discuss paper 1, Chemistry paper 1 of AS level Cambridge. Without further ado, let's just get started. Next, first question. In which option do all three particles have the same electronic configuration and the same number of neutrons? Here we are asked to find the row of particles that have the same electronic configuration and neutrons as each other. So first, before that, we have to discuss how to find electronic configuration. We just have to know the amount of electrons, basically. And to find the amount of neutrons, we have to subtract atomic mass with the protons. Let's discuss option A first, shall we? Okay. Option A, we have nitrogen with an atomic mass of 15, and amount of electrons of nitrogen is 7. Okay. So let's find the neutrons. 15 minus 7 equals to 8. Alright. Okay, so that's 8. Let's see if oxygen has the same. Oxygen here has an atomic mass of 16 with the amount of electrons is 8, which results in 8. Okay, same so far. Fluorine has, oh sorry, um, when I say electrons, I mean protons, guys. Correction. Okay, fluorine. Fluorine has 19 atomic mass of 19 and the proton of 9, which results in 10. Not the same. Alright, so we can eliminate option A then. Next. Option B, oxygen. This one has an atomic mass of 18 with an atomic mass of 8. We find that the neutron is 10. Okay, fluorine. Fluorine, just like we found before, is 10. Yes, 10. Neon. Neon has atomic mass of 20 with an electron of 10, which results in 10. Okay, the same. The electronic configuration of in row B is the same. Let's see if they have the same. Sorry, the amount of neutrons are the same. Let's see if they have the same electronic configuration now. Alright, for electronic configuration, before we do that, we have to see which atom has a charge. See oxygen here. It has a negative charge 2, while fluorine has 1. Okay, let's write the line here. Alright, now we have to find the electronic configuration. For electronic configuration, we just have to know the amount of electrons it has. We see that 8 oxygen has an amount of electrons of 8. However, because it is charged, negatively charged with 2, we have to add 8 with 2, which results in 10. So I'm going to write the electronic configuration. 1s2, 2s2, 2p6. Fluorine. Fluorine has 9 electrons. However, because it's partially charged with 1 here, charged with negative charge of 1, we have to add that, results in 10. The same. 1s2, 2s2, 2p6. Okay, consistent. Let's see the final one. Neon has no charge, so and its electrons are 10, which results in 1s2, 2s2, 2p6, making option B our answer. Next question. Methane and steam reactor produce hydrogen. 0.80 grams of methane and 1.35 grams of steam react. One of the reactants is used up. Which volume of hydrogen is measured at room conditions? So here we are asked to find the volume of hydrogen that is produced. The first step to find this is find the limiting reactant. We have to count the moles of methane and steam first. Here, the mole of methane is 0.005. Let's write that here. While steam is 0.075. Oops. 5. Okay. Oh, it's not appearing. There we go. Alrighty. Next, we just have to find the limiting reactant, the mole thing. We see that in the reaction here, it takes the steam is twice as much as methane, which means that it will take about twice the amount of steam to use all of the hydrogen, which is 0.10 if you multiply 0.05 by 2. However, we see that steam only has 0.075, which means that steam will run out first. Thus, steam is our limiting reactant here. Now that we found the limiting reactant, we just have to find the mole of steam. You see that between steam and hydrogen, there's a 2:4 ratio, or 1:2 if you simplify it. So that means we have to multiply the mole of steam by 2 because of this ratio, which will be 0.15. Let's just write it here. Okay. So approximately the mole of hydrogen is 0.15 because it's twice as much as steam. Now that we got all that, we just have to find the volume. Because it says it's measured at room conditions, we can just use V equals 24 multiplied by the mole. 24 multiplied by 0.15 will result in 3.6 cubic decimeters, which gives our answer B. And that's the fraction. Next question. The gas laws can be summarized in the ideal gas equation below. The volume of a sample of methane is measured at a temperature of 60 degrees Celsius and a pressure of 103 kilopascals. The volume measured is 5.37 times 10 to the power of negative 3 cubic meters. What is the mass of the sample of methane given to two significant figures? Here we are asked to find the mass, and we will use the ideal gas equation. However, before that, we have to convert some units first. Let's go with the temperature first. Temperature will be converted into Kelvin. So 60 plus 273 will result in 333 degrees Kelvin. Next, the volume measured, we have to convert into cubic decimeters, which is about 5.37 kilopascals. We will convert it into ATM, which is 1.03. Right, now we convert all of that. We'll just have to put it in the ideal gas equation. PV equals nRT. The pressure is 1.03 ATM multiplied by 5.37 equals the equation for mole is mass over molecular mass multiplied by the constant 0.82 and the temperature. The molecular mass of methane is 16. 0.082 times 333. 1.03 times 5.37. Excuse me for my bad handwriting once again. Okay, alright guys, so with all that, we just have to multiply it. Okay, 1.03 times 5.37 is 5.47 5.5315 multiplied by 16 over 0.082 multiplied by 333 is 27.306. Next, we will count 5.5311 multiplied by 16 is 88.4, divided by 27.306 is 3.24, which gives us the answer D. Next question. A 200 cubic centimeter sample of water has an amount of oxygen gas dissolved in it. The amount of oxygen gas is a volume of 6 cubic centimeters when measured at 1 times 10 to the power 5 pascals and 35 degrees Celsius. What is the concentration of oxygen gas in the water? Assuming that oxygen behaves as an ideal gas. To find this answer, we have to use the ideal gas equation, which is PV/nRT. Before we do that, we have to convert to units. Okay, 35 degrees Celsius. 35 degrees plus 273 is 308 degrees Kelvin. Next, we convert the pascals into ATM, which is 0.987 ATM. Now, we have to convert the volumes. For the oxygen here, 0.06. And for the water, it's 0.2. We converted it into cubic decimeters. Right, now we do that. Just have to count the concentration. To find the concentration, we'll just use, you have to divide the mole with the volume of the sample of water here. So we have to find a mole in this gas equation. So, and multiplied by constant, multiplied by the change in temperature. Okay. Oops. Okay. All right, now we put the pressure and volume. Let me increase the size over here. Pressure is 0.987 multiplied by the volume, which is 0.06. Let me just 0.006. Okay. Let me just squeeze this. Let me move it here. Alrighty. Now, let's try to multiply all of these. We will move the numbers. So 0.987 multiplied by 0.06, which is 0 there, over 0.082 multiplied by 308. Okay, let's try to convert. Try to calculate. 0.987 multiplied by 0.006, which results in 5.9 times 10 to the power of negative 3. We divide that with 0.082 times 308, which results in 2.34 times 10 to the power of negative 4. That's our mole there. Now we find our mole, we have to find the concentration. Volume, the volume, sorry, the equation for the concentration is mole over volume. We will use the mole, we will use the volume of water here. So 2.34 times 10 to the power of negative 4, sorry, over 0.2. Which results in, it's the volume, 1.17 times 10 to the power of negative 3. Giving our answer B. Next question. The structure of the sulfur dioxide molecule is shown. What is the shape of the sulfur dioxide molecule? So, we're here. We are given the structure of the sulfur dioxide molecule. Hold up, let me pull up my tool. Okay. Here the sulfur dioxide molecule. You're asked, define the shape. We have linear, nonlinear, pyramidal, and tetrahedral. First, we have to look at the structure. Here is structure here. The sulfur is connected with two oxygen atoms, bonded with two oxygen atoms, and has two free electrons. When we find a shape, we only focus on the central atom. So it will be about like this. Okay. And we have two more lines. Because they are not connected with, they're not bonded with any other atoms. This automatically causes a bent or V shape to this shape. You see here? Linear. Linear is not bent or V shape. It's straight line. So automatically it's wrong. Pyramidal tetrahedral. Pyramidal tetrahedral don't have four. I call them four lines in the shape over here. So automatically it's not pyramidal or tetrahedral. The option we left is non-linear. Next question. In which pair do the molecules have the same shape as each other? Here we have the options here, and we are told to find the molecules have the same shape. So each of these. Okay, let's start with option A. H2O has the shape of like this. Alright. With oxygen having two free electrons at the top. Okay. CO2. 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 So two oxygen atoms bonded with one carbon. Carbon has no free electrons at the top, which means it's not the same shape. We will eliminate option A. Next, B. Already have the shape in the show. Time to find the shape of SgXSCl2. Sulfur bonded with two chlorine atoms. Chlorine. When sulfur is bonded with two chlorine atoms, it has two free electrons at the top. Alright, it's the same shape, which means the correct option is B, ladies and gentlemen. Next question. A student makes 25 cubic centimeters of full mole per cubic decimeter hydrochloric acid with an equal volume of 4 mole per cubic decimeter sodium hydroxide. Initial temperature of both solutions was 15 degrees Celsius. The max temperature recorded was 30 degrees Celsius. Using these results, what is the enthalpy change of neutralization of hydrochloric acid? Okay, so here we will use the enthalpy change formula. Hold up, let me pull up my pencil. Okay, so the formula for enthalpy change is delta H over negative Q per N. Okay, let's find Q, which is mass times oh, what? Hold up. It's a bit error. Okay. Temperature change. Okay. So because it's mixed, the solution was mixed, we will combine both of the mass. So 25 cubic centimeters we will convert to 25 cubic decimeters, which is 0.025 times 2, 0.050. The heat capacity of water is 4.18. And you see that the change of temperature is 15 degrees Kelvin. Alrighty. Next, the result is 3.135 joule. Well, let me fix that number 5 there. Okay. Next, for the mole. To find the mole, we will multiply the concentration with the volume. We will not combine the volume we will not combine the volume from each of the compounds, by the way. We will use only one, which is 0.025, which results in 0.2. Hey, pardon me. Will result in 0.1. We will divide Q with N, which results in 31.35. Yes. Which we will round to 31.4, which is B. By the way, don't forget to put negative sign here. Next question. Carbon monoxide and methanol can react together to form ethanoic acid. Standard enthalpy change of combustion are given in the table. What is the value for the enthalpy change of reaction for the reaction between carbon monoxide and methanol? Alright, so for this question, we will use the formula. The H equals reactant minus product. We will use this because the uh, the data over here is given in enthalpy change of combustion, which uses this formula. Reactant is about negative 283. We will. Put up here, sorry. 283 plus negative 726. Pardon me for my bad handwriting once again, guys. Minus negative 874. Point 1, which is about negative 1009. Of course, negative turns to a positive, plus 874.5, which results in 134.9, which gives us B. Oops. B. Next question. A student mixed 25 cubic centimeters of 0.100 mole cubic decimeters sodium hydroxide solution with 25 cubic centimeters of 0.100 mole per cubic decimeters hydrochloric acid and noted a temperature rise of 2.5 degrees Celsius. What is the enthalpy change of the reaction per mole of sodium hydroxide? To find the answer, of course, once again, have to use the enthalpy change formula. Equation is delta H, the enthalpy change, negative Q per M. We will write, the equation here. Of course, we will change the 25 to cubic centimeters to decimeters, which will be 25 cubic decimeters, 0.025 cubic decimeters. We will add both. It will result in 0.05. Okay. Times 418 times temperature change, 2.5. We don't need to convert into Kelvin because it already set the difference in temperature, which is the same. The delta temperature. Okay. This will result in 0.5225. We'll return to negative. Okay, let's move. Next, the mole per volume times volume. Concentration is 0.100 or 0.1. Okay, we will write that. And it will result in 2.5 multiplied times the power of negative 3. Okay. This, when we divide both, it will result in, let's see, negative 5, 2 to 5 over 2.5, 10 to the power of 2, negative 209 kilojoules, which gives us the option A. Good job. Alrighty, y'all, let's move to the next question. Nitric acid is made industrially by the oxidation of ammonia, and the equation for the process is shown. And the process happens in 3 stages. Equations in enthalpy change for these stages are given. What is the enthalpy change for the process shown in equation 1? Alrighty, so we have to find the enthalpy change of the equation 1 here. First step is to basically just analyze and compare the stages in the equation. We see that in the equation, oxygen is twice as much as in equation 1, oxygen is twice as much as stage 2. So that means you have to multiply oxygen here. That means this is now 4NO and 4NO2. So that means stage 2, the enthalpy change is multiplied by 2. Okay. Of course, you may see like they have different amounts as well over here, but that's for later, okay? Next, we have to find this first. Next, we just combine all of the stages. Let's put it in the corner here. H3 plus 5O2. If you're wondering all this time why my handwriting is bad, it's because I'm writing on my phone. That's not as easy. Okay. And 2 plus 2 plus, 4 because it's multiplied by 2. Plus, plus oxygen plus 4NO2 plus oxygen plus 2H2O. First, I have to. Okay. Let's just move it. Maybe move it down here and make it easier. Oops. It's 2. Now we write what's in the right hand side of the equation. So 4NO plus 6H2O plus 4NO2 plus 4HNO3. Okay, like that. Now it's time to eliminate. We see on the left and the right hand side, the ones that are the same are 4NO2 and 4NO. So we cross them off. 4NO2. 4NO2. 4NO. Oh, sorry, there seems to be a mistake here. I wrote NO2 twice, so this is NO, just NO by the way. NO plus 2. Okay. Okay. There we go. Right. Now that we eliminate that, it's time to write the rest. So 4NH3 4 hold up, let me write that. NH3. We add the oxygen molecules up, it will result in 8. Oh, my mistake once again, no. I wrote 2 here. Okay, so it will result in 8O2. And okay, that's all I think. Yep. Oh yes, plus 2H2O. Forgot about that. Next, the right hand side of the equation. It's 6H2O plus 4HNO3. Let's compare it with the equation 1 here. We see that only H2O is on the right hand side. Meanwhile, there's H2O here. That means we subtract H2O, 2H2O here to get to 6, which results in 4. Alright. We notice that all of these particles can be divided by 4, simplified. Divided by 4, which results in NH3 plus 4O2, 4H2O plus NHO3, which matches with equation 1. Alrighty. Now that we got our data, we know what to do. Now we just have to count the enthalpy change. You see that here we multiply stage 2 by 2, the enthalpy change for stage 2 by 2, and divide the results with 4. So enthalpy change equals to enthalpy change is about 904 plus 114 multiplied by 2 plus negative 348. Alrighty. Which results in negative 1480. Of course, we divided by 4 here, that means we have to divide it by 4 here as well. Which results in negative 370. Making our answer for this question B. A sample of magnesium contains the isotopes magnesium 24, magnesium 25, and magnesium 26. Which the percentage abundance of magnesium 25 and magnesium 26 is the same. The relative atomic mass of magnesium in the sample is 24.3. What is the percentage abundance of magnesium 24? Here we are asked to find the percentage abundance of magnesium 24. Alrighty. So first, what we have to do is we have to make like a formula for the abundance of magnesium 24. Okay, so let's say the abundance of magnesium 25 and 26 are X. Oops, that one. They are the same, of course, so yes. And just put them in one variable. So abundance, the total abundance is 100. So abundance of magnesium 24 is 100 minus X or about 100 minus 2x's. Alright, there it is. So we found that. That's the 4 magnesium 24. Now we just use the formula for relative atomic mass. We will put it in here. Okay. We will put this formula somewhere. But there we go. Okay. Sorry. Next, use the formula for relative atomic mass, which is AR. So that name AR. I'm gonna make it smaller. Okay, let's just put it in the corner there. Okay, now AR equals to sigma percentage of abundance plus isotope over total abundance. Alrighty, so that's it. Oh. Excuse me for my bad handwriting. Okay, let's see. The atomic mass 24.3. Okay. 24.3. Let's find the 12 ones. 24 times 100 minus 2x plus minus 2x plus 25 multiplied by x plus 26 multiplied by x. Okay. Oh yeah, over 100%. Okay, we put that there. Oh, nope. Okay, we multiply both sides by 100. 2400. 2400 minus 48. It's a bit laggy. 48x plus 25x plus 26x, which will, oops, love y'all. Let's put it up here. Result in 2,430 equals 2,400 plus 3x. We move the numbers here. 2,430 minus 2,400 over 3 equals x, which results in 10%. Alrighty, found the x. Now we just gotta find the percentage of abundance. So if 25 magnesium 25 is 10, magnesium 26 is 10. Magnesium 24 is 100 minus 2x, which is about 80%. Thus, the answer to this question. Next, A student calculated the standard enthalpy change of formation of ethane, C2H6, using a method based on the standard enthalpy changes of combustion. He used correct values for the standard enthalpy change of combustion of ethane and hydrogen, but he used an incorrect value for the standard enthalpy change of combustion of carbon. He then performed his calculation correctly. His final answer was negative 158. What did he use for the standard enthalpy change of combustion of carbon? So here we are asked to find the enthalpy change of carbon. First step to find this answer is, let's move it to the top left. Carbon atom. There's a hydrogen atom. C2H6. That means we multiply hydrogen by 3 and carbon by 2. Just like that, right? The enthalpy change for this is negative 408. Next, you have to just write the reaction for the enthalpy change of combustion of carbon and hydrogen. So carbon is C plus O2. This results in CO2. Of course, we're trying to find this. This is variable. Next, hydrogen. 0 half oxygen results in H2O. Next, we'll just have to write the reaction for the enthalpy change of formation. The enthalpy change of combustion of ethane. Let's put it over here. So C2H6 plus oxygen multiplied by 7 divided by 2, and that will produce CO2 plus 3H2O. And the change is negative 1560. Alright, now that we write all that, let me write the enthalpy change for hydrogen here. Negative 286. Okay, now that we got all of this data, we have to apply Hess's law. So, to form ethane, we need hydrogen and carbon dioxide. All right, let's put it here. So enthalpy change of formation of ethane equals twice the amount of CO2, right? So that means it's twice the amount of over here plus, let's make that smaller, so over here plus three times the amount of hydrogen. So it will be about 3 multiplied by negative 2 over 3 multiplied by negative 2H6. Let's make that a bit smaller. Okay, let's zoom here. Alright. Of course, there is, don't forget, enthalpy change of combustion of ethane. So we subtract it, which is about negative 1.6 from 0. The enthalpy change of formation method is negative 158. Negative 158. Okay. We will calculate that. So it will be 2x plus 3 times negative 286 is negative 858. Negative 858 plus 1560, which is with the numbers around of 1x. So negative 858 plus 1560 is 702. We move 702 to the left. So it will be negative 702. Oh boy, it's getting messy here. Okay, we'll just do this. Negative 158 minus 702 equals to negative 860 divided by 2. Right? Negative 800 divided by 2, which results in negative 430, giving us the answer of C. Next question. The enthalpy change of neutralization of NHO3 with sodium hydroxide is negative 57 kilojoules per mole. In experiment, 20 cubic deciliters of 4 mole cubic deciliters NHO3 is mixed with 30 cubic centimeters of 2 mole per cubic deciliters of sodium hydroxide in an insulated container. The initial temperature is 25 degrees Celsius. It can be assumed that the heat capacity of the product mixture is 4.2 joules per cubic centimeters per Celsius, and that there are no heat losses. What is the maximum final temperature of the mixture? Solve this equation. First, let's just move the question to the top left. We will have to write out the reaction here. Okay, so let's write NHO3 plus sodium hydroxide 2, which results in Na water. Okay. We count the moles first by multiplying the concentration of the volume each. NHO3 has a concentration of 4 and a volume of 0.20 cubic centimeters, which is we divide by 1,000, which results in 0.02. 1, 2, 3. Yeah, 0.02, which is 0.0. Next, for sodium hydroxide, which is about 2 and 0.03. That's about it. 0.06. Okay, now we got the mole. We have to calculate reaction. Initial reaction, the final product. Of course, you will write the moles here, 0.08, 0.06. Of course, these don't have any moles because they haven't existed. Next, for the reaction, we look which is the smaller amount, which is 0.06. So 0.06, 0.06, these will appear 0.06 and 0.06, 0.02. NaOH runs out. We can conclude that NaOH is the limiting reactant, which we will use in when we calculate for the enthalpy change. Okay, enthalpy change. Of course, we were asked to find the final temperature of the mixture. To find that, we have to write down the enthalpy change formula first. Okay. Q. Alright. We already have the data here. The enthalpy change is about negative 57. You already have the mole, which is 0.06. So we'll just do this. Enthalpy change equals negative Q per N. Hold up, let me write that. Negative Q per N. Of course, to get negative Q, we can just multiply the enthalpy change with the mole, which is negative 57 times negative 57 with 0.06, which is about 3.42 kilojoules. We see in the question, it is in joules, the heat capacity. To match, so it will be the same. Let's just convert it to. Okay, we got the energy here, the Q here. Next, we'll just need to find the temperature. Q, plug in the full equation, which is Q equals mass times heat capacity of water times the change in temperature. Okay. Alrighty, so we'll plug in 3, 4, 20 times. Run both. By the way, we won't change the mass here because the heat capacity is in cubic centimeters as well. So 4.2 times, let's say A minus 25, because 25 is the initial temperature, according to the equation. Okay, so it will be 210 delta T. Oh wait, let's do not cause confusion. Delta T. So 210 delta T. 3420. 3420. 210 delta T. Oh, sorry. 210 delta T. Okay. Okay. Well, let me just erase that real quick. Okay. So let's see. Okay. The result will be 16.3, the temperature change. 16.3. The initial temperature is 25. So we'll just oopsies. Yeah, so we'll just add the 25 with the 16.3. 25 plus 16.3 for the maximum temperature final here. Temperature final will be about 41.3, which gives us the option of C over there. We will move on to the next question, which is about another enthalpy change question here. The standard enthalpy changes of combustion of glucose and ethanol are given as negative 2,820 and 1,368 kilojoule per mole respectively. Glucose can be converted into ethanol. What is the standard enthalpy change for this reaction? Alright, first let's just count here. Look, there's another error here. Okay. Let's count. You see, for glucose, negative 2,820. Alright. However, see that they have a coefficient. So that means we multiply the enthalpy change by 2, which is about, so 1,368 multiplied by 2 is 200,736. Here, carbon dioxide has 0 enthalpy change, by the way. Okay, so we will try to count the enthalpy change. Because it's combustion, it's given in combustion, we will use the combustion formula. Hold up, I can't write it wrong. Hold on. Okay. React minus the product. Okay. The reactant is 2,820 minus a negative. Don't forget to put the negative. 2,376, which is about 84 kilojoules. But let me fix that for. Which gives us the option of B. 4 mixtures are added to 4 separate 50 cubic centimeter samples of water and stirred, which most results in a solution with the highest pH. So highest pH over here means the most alkaline, most basic. Okay, so we need to find a solution that makes it have high pH. If it's mixed. First, we look at option A, aluminum oxide. Aluminum oxide is apathetic. While aluminum chloride is not an acid. It hydrolyzes water. Which will result in an acidic solution, which we don't want. Okay, A is eliminated. Next, magnesium oxide. It's a base. While magnesium chloride is neutral. Mix the two together, of course, will result in a basic solution. Okay, C? What about C? C has phosphorus oxide, which is acidic. And phosphorus chloride hydrolyzes, which produces acid solution, which we don't want. Next, weak acid is silicon oxide, of course, and silicon chloride hydrolyzes, which makes the solution acid. So that means the correct option is B. Okay, we're now in the third final question. Which mixture will react to form exactly 1 mole of water? Here we're given the volumes of the particles here with their volumes. We have to find which will result in 1 mole of water. Find this, we have to calculate the moles. By the way, we will just go straight to the answer, which is B. Or it's why B, I will explain it. It's okay. I will read. Sorry. Okay, well. 1, 2, 3. We are now in the third final question. Which mixture will react to form exactly 1 mole of water? Here we are asked to find which mixture react with to produce 1 mole of water. Okay, so we'll just go ahead and answer this, which is B. Why B? Well, we will explain it right now. Let's move here. Okay. All right, why is it B? Well, we'll explain. Here in option B, the volume is given as 250 for H2SO4 and 100 for sodium hydroxide. To find which reaction will for 1 mole, we have to find the moles of each of these particles. So, to find it, we have to multiply the volume with the molecular mass, with the concentration. So it will be about, because it's in cubic centimeters, you have to divide it by 1,000. So it's 2 times 250 divided by 1,000 will result in 0.5. This goes the same for the other particle, sodium hydroxide. So sodium hydroxide, 1, yes, 1 times 1,000 over 1,000, which results in 1. That's the moles of each of these particles. Next, we have to write the reaction. So, look, H2SO4 plus NaOH, sodium hydroxide, will produce. By the way, we will multiply this by 2 to equal, make it equal. And sorry, because it will produce Na2SO4. That's why you multiply the NaOH by 2. Plus H2O plus 1 2 plus. All right. Now that we got that the reaction is right, what happens in the reaction? In the beginning, there's 0.5 moles of H2SO4 plus 1 mole of sodium hydroxide. Of course, this is before the reaction occurs, so there's none for products here. The reaction. In the reaction, we see that usually we will subtract it with the smallest amount of moles here in the reaction, because it will run out first. However, see that 1 mole here is for 2 sodium hydroxide. The amount is twice as much. So that means we'll just divide. We just subtract. That's 1. Na2SO4 is only 1, so 0.5. Well, H2O is twice as much, so it's 1. Products are finished or used up. Result in 1 mole of H2O. So that's why the answer is B. So that means if we calculate, let's see, the volume of NaOH here, 500, it will not result in 0.5 because 0.5 is for both of of the sodium hydroxide. It will result in 0.5 of H2O, which is wrong. All right. Next question. Aqueous acid P and aqueous alkali Q have the same concentration. 20 cubic centimeters of P is added to a canonical flask. Q is slowly added to the flask, and the volume of Q and the pH are recorded. Alrighty. So which gives the identity of P and Q. We are also given the pH saturation here of the result. Alrighty. So we are here to find the identity of P and Q. Which one is which? Let's start with discussing each of the options. Option A, we have hydrochloric acid, Vahya, and sodium hydroxide. Both both are strong. However, both only release one ion of molecules. We see here in the pH saturation curve, it takes 10 cubic centimeters needed to neutralize the pH. So Q must be twice as powerful as acid because it does its job by neutralizing it, making it more basic, with half of the volume of Q here added. So because both will release one ion molecule, they need to be equal volume to neutralize. So eliminate A. B. B is a weak base, a strong acid. It cannot result in this much change in the pH. Eliminated. Now it's C. Barium hydroxide releases two OH ions, while hydrochloric acid releases only one one hydrogen ion. Because it's 2 times strong, you only need half of the volume of the base here to get the pH into a very basic state. So the answer is C. What about D? Well, D is a weak acid and a strong base, which can result in a change of pH upwards, but both have to be strong, so it cannot be D. Result is C. Alright, we move to the final question in paper 1 here. Sulfur dioxide is used as a preservative in winemaking. The following question describes the reaction that occurs when sulfur dioxide dissolves in water. Which statement about these two reactions is correct? So we need to find the statement that is correct about these two reactions. So let's discuss once again each of the options and see which one is correct. First, HSO3 acts as a base. Let's see if it's correct here through the equation. We see that HSO3 is in the first equation, right? Alright. So we see that SHO3, H2O, let's start from the left. H2O plus SO2 will result in HSO3 and a hydrogen ion. We see that, of course, sulfur dioxide. The sulfur dioxide receives the hydrogen ion from H2O, making HSO3, and leaving hydrogen ion alone. Of course, the sulfur dioxide also takes in the oxygen here, which makes HSO3 a hydrogen ion receiver, which makes it a base. Okay, correct. Let's see about B. SO2 acts as an oxidizing agent. Let's see the equation. From the equation, SO2, there is no change in electrons in SO2, which means it's not an oxidizing agent, so we will eliminate that. Next, SO3 acts as an acid. Of course, we know SO, SO3, that's an acid. That means you have to donate a hydrogen ion. However, in the equation, SO2 does not have a hydrogen ion atom to lose, so it cannot donate an ion. So therefore, it's not an acid. Eliminate. Sorry about that. Eliminate option C. Next, option D. SO3 acts as a reducing agent. We will see from the equation there is no difference in electrons. There's no change in electrons, which doesn't make it a reducing agent. So we will eliminate D, which means that our answer is A. HSO3 acts as a base. Dua, tiga. Hello everyone and welcome to another video of Chemistry ASA Level Cambridge. Today we will discuss questions in Paper 2. Without further ado, let's just get started. Okay. First question. Electrons in atoms up to krypton 36 are distributed in sp and d orbitals. Say the number of occupied orbitals in an isolated atom of krypton. Okay, so krypton has up to 36 electrons. First step, we have to find the electronic configuration over here. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. Now we just have to see the number of orbitals. In the s subshells, there are 4 s subshells. There is 1s, 2s, 3s, and 4s. And each of this subshell has 1 orbital. 4 times 1 is 4. So that's for the s orbital right there. Next, for the p subshell, we got 3 p subshells. 3p6, 2p6, and 4p6. In each of these subshells, it has 3 orbitals. 3 times 3 is 9. Okay. For the final one is the d orbital. The d subshell, there's only one, which is 3d10. And each subshell has 5 orbitals. 5 times 1 equals to 5. Thus, the answer for S is 4. Let me write that down. Is 4. For P is 9. And for D is 5. Okay. Next question. Describe how an atom of chromium-54 differs from an atom of chromium-52. Refer to the number of particles in your answer. We see that the isotopic mass of chromium-54 and chromium-52 is different, which means that they have different number of neutrons. So the answer is the total number of neutrons in chromium-52 is 2 less than the neutrons in chromium-54. Okay. All right. Next. Deduce the total number of unpaired electrons in an atom of chromium. Chromium has this electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 35. So it has about, let's see, 10, 12, 18, 19, 24. It has 24 electrons. Let's see which one is unpaired. So see in the 4s1 here, there's only in the s subshell, in the s orbital, there is only there's only uh, in the orbital there's only there will be two occupied electrons. So see that there's only one. That means one is not paired. 3d5. In 3d5 it has five orbitals. You see that there's only five electrons, which means that there's only two paired and there's two not paired. So the answer is 3. There's 3 not paired electrons. Alrighty. Next, most elements exist naturally as a mixture of isotopes, each with their own relative isotomic mass. The mass spectra of an element reveals the abundances of these isotopes, which can be used to calculate the relative atomic mass of the element. Magnesium has 3 stable isotopes. Information about the two are given. The relative atomic mass of magnesium is 24.3. Calculate the percentage abundance and hence the relative atomic mass of the third isotope of magnesium. Give your answer to 3 significant pairs. So you're told to find the isotomic mass and the percentage abundance of the third isotope. Okay. So we know that first of all, we know that the total abundance is 100%. So we could just 100 minus 79 minus 11 leaves 10, means that this third isotope of magnesium has an abundance of 10%. Okay, now we just input in the relative atomic mass equation. Atomic mass equals sigma percentage abundance times isotopes over the total abundance, which is 24.3 equals to 79 multiplied by 24 plus 26 multiplied by 11 and 10 multiplied by x over 100. We multiply both sides by 100, which results in 2430 equals to 79 times 24 is 1896 plus 26 times 11, 286 plus 10x. 1896 plus 286 equals to 2182. And then we move it to the left hand side to subtract it, leaving with 248 equals 10x. We move the 10 to the left hand side, so it's 248 divided by 10 equals to 24.8. So the isotomic mass of the third isotope of magnesium is 24.8 and the percentage abundance is 10%. Okay, next. Define relative atomic mass. The relative atomic mass is the weighted average mass of atoms in a given sample of an element compared to the value of the united atomic mass unit, which is 1/12 of the mass of carbon atom. Next question. Table 2.1 shows the abundances of two of the isotopes present in the sample of iron. Use table 2.1 to calculate the relative isotomic mass of the third isotope of iron in the sample. Show your work. So here we are told to find the isotomic mass. We are given the atomic mass here in the previous question, which is 55.8. Just like we did before, first we find the abundance, which is easy. We just subtract 100 because the total abundance is 100. So 100 minus 91.9 minus 6 is 2.1. Now we put it in the relative atomic mass formula, which is 55.8 equals to 53.9 multiplied by 6 plus 55.9 multiplied by 91.9 plus x multiplied by 2.1 over 100, which results in 55.8 equals 323.4 plus 5,137.21 plus 21x over 100. We multiply both sides once again like before with 100, which results in 5,580 equals to 323.4 plus 5,137.21, which equals to 5,460.61 plus 2.1x. We move the number here to the left hand side, which results in a 5,580 minus 5,460.61, which results in 119.39. Okay. And then we move the 2.1 to the left-hand side, which results in 119.39 divided by 2.1, which results in 56.85, which is our isotopic mass. Next question. Deduce the number of pairs of electrons in the 3D subshell in an iron 2 ion. We know that iron has the electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. So it's about 10, 12, 18, 20, 26 electrons. But because it has an ion, a positive charge of 2, we subtract the amount of electrons, which results in ending in 3d6. So we are told in the question, we are asked to find the number of pairs of electrons in the 3D subshell. The 3D subshell, the total of electrons in the 3D subshell is 10 max. However, we only have 6. Here we draw the orbitals, which are 5, and the electrons. You see that when we add the electrons, there's only 1 paired and 4 unpaired, meaning that the number of pairs of electrons in the 3D subshell of an iron 2 ion is only 1. Next, define enthalpy change of formation. The definition is the enthalpy change when 1 mole of a compound is formed from its element under standard conditions. That is the enthalpy change formation. Alright, moving on to the next question. Iron 3 is made when iron 3 oxide is heated with carbon monoxide, as shown by reaction 2. Table 4.1 shows enthalpy change formation data measured at the 298 Kelvin and 101 kilopascal. Complete table 4.1. Right, we already did that. Next, use the data in table 4.1 to calculate the enthalpy change of reaction. Show your working. So, we have to count the enthalpy change for this reaction. We already got the values here, so we just have to plug it in. We see here. Let's compare the reaction with the equations here. So, see that our iron 3 oxide remains the same. Okay, so it's negative. Plus 3 carbon monoxide. However, we see that here carbon monoxide is only 1 for negative 110.5 enthalpy change. So we have to multiply negative 110.5 by 3. Next, for carbon dioxide, we see that here in the equation, carbon dioxide, there's 3. However, in the equation, negative 393.5 is for 1 carbon dioxide, so we have to multiply it by 3, which results in 1180.5. Now we'll just have to plug it in the equation, which is enthalpy change equals enthalpy change of products minus enthalpy change of reactants. The products are carbon dioxide and iron, but iron has no enthalpy change, so it's 0. And the reactants are carbon monoxide and iron trioxide, so it's negative 1180, negative 1180.5 minus negative 110.5 multiplied by 3 minus negative 824.2. We see the results, negative 180.5 plus 231.5 plus 824.2, which results in negative 24.8 kilojoules per mole. That's our enthalpy change. Next, sulfur has about 16 electrons, so write the electronic configuration. 1s2, 2s2, 2p6, 3s2, and 3p4. Next, chlorine. Chlorine has about 17. 1s2, 2s2, 2p6, 3s2, 3p5. Okay, now that we got that, we just have to see the outermost electrons, which are these. For sulfur, there is about 6. So write 6. 1, 2, 3, 4, 5, 6. Chlorine has 7. Sorry, write that. 1, 2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Alright, that's all we need. Next, predict the shape of and bond angle in the molecule by using VSE pair theory. According to the bonds and number of free electrons, this shape is bent or V shape, which has a bond angle of 104.5. We move over to the final question, which is Table 1.1 gives data relevant to the reaction of chlorine with ammonia. Here we have a data table of ammonia, which has an enthalpy change information of -46, while hydrochloride gas has -92. Use the data in the table to calculate the enthalpy change in reaction of chlorine with NH3. Okay, so we put in the equation, which is Cl2 plus NH3, which results in nitrogen gas and the hydrochloric gas here. Of course, we stabilize it, which results in 3Cl2 plus 2 NH3 equals N2 plus 6 HCl. We just have to count the enthalpy change of the products first. For nitrogen, there is 0 enthalpy change. For hydrochloric gas, there is -92. But because there's a coefficient of 6 here, we multiply it by 6, which results in -552. For the reactants, we have chlorine. However, of course, chlorine has 0 enthalpy change, while ammonia does. -46 here. But because there's a coefficient of 2, we multiply it by 2, which gives us -92. Now we just have to count the enthalpy change of the reaction, which is product minus reactant equals to -552 minus -92, which results in -460. And that is our final answer.